Okay. Hmm. Okay, so it's getting recorded. Okay, so today we want to prove something. So what? Let me recall the essence of what we have done. Okay, so this is for my reference. So we proved the following. So we take, we take sigma, which is a compact metric space. We usually something contained in C. Okay, compact. Then if we have if pi is a representation, C of sigma to some d of h, okay, is a representation, which means unital star representation, star homomorphism from the C of sigma to B of h. Then there exists a measure. So any doubt from the last class about this measure construction and all that? So how we do that is, if you have any representation of pi of sigma on some h separable, which is separable, then there exists a sequence of measure. There is a countable family of measures such that the pi is unitarily equivalent to direct sum of pi mu n, where pi mu n is just the multiplication representation of L2 mu n. So this h looks like direct sum of L2 mu n using a unitary. I mean, it's not exactly equal, but it's up to a unitary. This h looks like L2 of mu n, direct sum of L2 of mu n, and each L2 of mu n, this pi mu n acts as multiplication operator. You take the direct sum of all those representations. That is what this representation pi will look like. Okay, then you, by using that mu n, you take some positive numbers, epsilon n greater than 0 for each n. Then you would use this single measure, okay, where summation epsilon n equal to 1. And remember that all these mu n's are probability measures because of because it's all cyclic representation. You can take the cyclic vector to be unit vector. So you take this measure mu, and using this, we get a single representation on this L2 of mu. Okay, and by this unitary, we'll bring it back to the H. We have a unitary which intertwines this pi and direct sum pi mu n. So then we intertwine that to bring it as a single representation, and each pi mu n can be extended to pi mu n tilde. I mean, which is again a multiplication representation. So there exists a measure mu on this sigma and a representation pi tilde. So this is abstract representation pi tilde from this L infinity of this mu to this B of h again, okay, which is an isometric representation, such that if you have a family Fn contained in L infinity, such that this is uniformly bounded, and Fn converges to F in mu, okay, then pi tilde of this Fn converges to pi of F strongly. That is point-wise convergence. Pi tilde Fn of xi converges to pi of xi for all xi in Hilbert space H. Okay. So this is what we have proved. Okay. Now we want to use this to prove something called spectral mapping theorem. You can call this a spectral theorem also, because that will follow from this. But we will prove the spectral theorem for normal operators directly. So at that time, it will include the self-adjointness also, self-adjoint case also. So here we are proving it for self-adjoint case. So this is theorem. So let x, then maybe I take t, because there will be small x coming. So t in B of h, self-adjoint. This is for self-adjoint operators. For normal operators, we have to work a bit. We have to do something more. So this is for self-adjoint operators. Okay. Then such that sigma of t equal to the sigma contained in real line. Since it is self-adjoint, the spectrum is contained in real line, which we have proved. Okay. Then 1. There exists a homomorphism, isometric representation. So which we denote by this from C of sigma. F is here. This is, I mean, you can call it pi, but let us use this following notation: f of x. Okay, I mean this f going to pi of f. That pi of f we are calling it as f of x. Okay, this notation is consistent. If you have a polynomial, then you can write a polynomial in x, this operator in x, and that is what we are calling as p of x. So here, if you have a continuous function in sigma, then you get a corresponding representation. I mean, you have a representation pi from c of sigma to this b of h, and that pi of f you are calling it as f of x. So, I mean, what I'm saying is the following: if you have a pi is a representation from c of sigma to this b of h, okay, then this f going to pi of f. This pi of f we are calling it as f of x. Okay, it's just a notation. Okay? There exists a unique isomorphic representation such that such that I don't know whether I missed some things. So f0 of x equal to x, where f0 of t equal to t. Okay. Yeah, that's all. 2, there exists a measure mu on the sigma such that, and I mean, okay, this is what is called continuous. Let me write here. The map x going to this f of x is called continuous functional calculus. For x. Okay. This is what is called continuous functional calculus for x. I mean, we use this term freely. Let f be the continuous functional calculus or something. Two, there exists a measure mu on sigma and a unique isometric representation. No, let me not say. You need an isometric representation like this. So from L infinity of sigma mu f going to this f of x in b of h. Okay. Extending the continuous functional calculus. I mean, you can say it's extending the continuous functional calculus, or you can say that this condition is enough. I mean, this will determine the continuous function such that f0, I mean, this f0 of x equal to x. Okay. I mean, this condition will uniquely determine this map, this f going to f of x. Okay. Further, I mean, it is isometric. Further, if fn supremum of n smaller than infinity and fn converges to f in mu, in measure mu, is equivalent to saying fn of x converges to f of x strong. Okay. 3, this L infinity sigma mu is uniquely determined. That is, if there exist two measures mu1 and mu2 on sigma satisfying the 2, then mu1 and mu2 are mutually absolutely continuous. That is if mu, that is mu1 of E equals 0 is equivalent to mu2 of E equals 0 for all. I mean, for any E in the sigma algebra of that sigma. So this means that is this L infinity sigma mu. This L infinity space does not, I mean, it depends only on the, it depends in the measure class of mu. Measure class means it's all those measures which are mutually absolutely continuous with respect to mu. It only depends on that measure class. It's not, so L infinity is uniquely determined. So, I mean, this, usually LP spaces are not, it depends on the measure. But L infinity space depends only on the measure class, so-called measure class. That is, if you two measures mu1 and mu2 are absolutely continuous, then the L infinity, that is the same function. Okay, it's not that they are isomorphic. It's just the identity map is an isomorphism. Okay, they have the same functions. So the L infinity is uniquely determined. This algebra, this is a Banach algebra, C star algebra, and that is uniquely determined. Okay, so these are the three things. I have written too many things, but the proof, we have already proved everything. Okay, the proof. So first statement says that there exists an isometric representation from C of sigma to B of H satisfying that condition. So we have already proved it. So you take this, I mean, let P in C of sigma be a polynomial. You have already proved it. I'm just recalling it. Okay, then consider this map P in C of sigma to P of X. Okay. So this map, we have already proved that this map is isometric. That is norm of P of X equal to spectral radius of P of X. Okay. That is just equal to spectral radius of P of X equal to supremum of T, and supremum of T in sigma of P of X. But that is same as supremum of P of T. That's the T in sigma of X, okay, which is norm P. I mean, norm P in the C sigma. Let's write the next piece. Okay. So this is a isometric representation. I mean, it's usually contractive. Any homomorphism between C star algebra is contractive, but here it's isometric representation. Just to prove the isometric, I just wrote this. So this implies this map P going to Px extends as an isometric representation. Just a, I mean, so you have to prove that it's also, I mean, see, the point is, if x going to xn going to x, then xn star goes to x star. If xn goes to x and yn goes to y, then xn yn goes to xy. And because of all these things, this extension is also a homomorphism. It's also a star homomorphism. Okay. So I mean, those things I don't want to write, and which is clear. So extends as an isometric representation. Which we denote by x going to f of x. Okay, that's all. So we have proved. I mean, it's clear. Okay, so if you have any t, then so I'm sorry, this is a t and x I have mixed. So I have to call it as, maybe I will change this to x here. Okay. So continuous functional calculus is proved and it's clear. So if you have any continuous function on the spectrum, then we can make sense of f of x. Okay. Earlier we can make sense for a polynomial. Now we can make sense for any continuous function. Okay. So that's what this theorem says. Now we can talk about measurable function. Then now we can extend this to L infinity, and all these things are already proved. You have a representation which you want to call, if you want, you can call it as pi. Then you have a representation pi tilde defined on that. So call that pi tilde as the measurable functional calculus. So this is what is called measurable functional calculus. So this map x going to x in L infinity going to this f of x is called measurable functional calculus. Okay. This is what is called measurable functional calculus. So we have already proved everything. So we have proved that if you have pi is an isometric representation, and we have already proved even otherwise it extends to isometric representation. Even when it is not isometric, it extends to an isometric representation on every. Okay. So we have proved everything. It's unique. Uniqueness we have to prove. No? Is there anything new to prove uniqueness? We have already proved that if you have any pi, then there exists a pi tilde. That we have proved it, no? In the last class that the pi tilde is unique. That follows because if you take any continuous function, the uniqueness follows from this. Uniqueness, if you have any, there exists continuous function fn in C of sigma, such that fn converges to, if you have any f in L infinity, okay, fn converges in mu to in mu. Okay. But then pi of fn, then this fnx converges to f of x strongly. Okay. So because of, but then this fnx is continuous. This is the continuous functional calculus. Okay. So the strong limit is unique. So f of x is uniquely determined. Okay. This implies f of x is uniquely determined. I mean, it's a unique extension of the continuous functional calculus. You have continuous functional calculus, and this measurable functional calculus is uniquely determined by this, by this, because of this. Okay? Continuous functional calculus. It's okay. Okay, so all these things are clear. Okay, so now I want to prove the uniqueness of the measure. It's not uniqueness of measure. If you have two measures, then they are mutually absolutely continuous. So the L infinity is unique. Okay, the measure is not unique. Even though the measures are not unique, the L infinity is unique. Okay, suppose mu1 and mu2, two measures satisfy 2. Okay, so satisfy 2 means if you I mean you have the extension to L infinity mu, and then the strong convergence criterion, whatever the convergence criterion we have, that is satisfied. Okay, satisfy 2. So then define a new measure mu equal to mu1 plus mu2 by 2. This is, which is again a probability measure, and so suppose if fn converges to f in mu, then fn converges to f in mu I for I for all I equal to 1 and 2. Okay? For I equal to 1 and 2. Okay. I mean, that's clear. Okay, because whatever you I mean, that will be mu1 converges in measure means fn, this fn, I mean this set mu of fn minus f greater than or equal to epsilon. This set should go to 0 for each epsilon as n goes to infinity. But then this is equal to sum of those two measures, and if this goes to 0, then they are positive, so they are less than that. That should go to 0. Okay, it's otherwise also true, but we will use only this way. Okay. Now choose Fn, which are continuous function in C of x, because for any measure we can do this. That's what we have proved earlier. Okay, such that Fn converges to F in nu. Okay. Then Fn converges to F in mu A for I equal to 1 and 2. Okay. Okay. So because of this, so let pi 1 and pi 2 are two representations. I mean, not two representations, are representations of L infinity sigma mu 1 and L infinity sigma mu 2, okay, extending continuous functional calculus. Okay. Then for, oh, okay, so now I don't want to use it for M. Choose this. No, I don't want to do this. Let me write. Let E be some set in a Borel set in sigma. Okay, choose Fn continuous function, which we proved it using Lusin's theorem. Fn consider continuous function C sigma such that Fn converges in nu to 1e, which is possible because it is in L infinity. We can do this. Okay, so then Fn converges to in mu I to 1e for I equal to 1. Okay. So this implies pi of Fn. This Fn's are continuous function. So this pi 1 of Fn and pi 2 of Fn both are same because they both are extensions of this continuous functional calculus. Okay. Now pi 2 of E, pi 2 of 1e. Okay. Pi 2, I mean, it's a representation of L infinity with respect to mu 2, pi 2 of 1e equal to this limit, strong limit. Strong limit of pi 2 of Fn. But then they agree because Fn's are continuous, they agree, pi 1 and pi 2 agree. Okay. As they are in, as Fn's are continuous function. Okay. Now this also goes to this, so pi 1 of 1. Okay. So if mu 1 of E equals 0, of course mu 1 of E equals 0 is equivalent to saying 1E is 0 as an element in L infinity of mu 1, right? That's what it means. Okay. So this implies, since that is isometry, this implies pi 1 of 1e equals 0. That's what it means. Okay. And this implies by this, whatever the computation we have done, pi 2 of 1e is also equal to 0. Okay. But that is equivalent to saying mu 2 of e is also equal to 0. Okay. So mu 1 and mu 2 are absolutely continuous. So, I mean, you can reverse the argument if you want. Mu 1 and mu 2 are mutually absolutely continuous. Okay. So we have proved the theorem. I hope it's all right with everyone. I mean, if you have any doubt in this theorem or in the previous class, whatever you have done, you can ask me now. So we will go to something new. This is okay. So till up to here for midterm exam. Okay. Okay. So the syllabus for midterm exam is up to here. I mean, up to this theorem. Okay. So this is okay.
Okay, sir.
Yeah, no, it's fine. Okay. So, 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 so we have proved some spectral mapping theorem for self-adjoint operators. Now we want to use this to prove spectral mapping theorem for normal operator. And we use the spectral mapping theorem. See, the spectral mapping theorem gives the following. If you have any set E in the sigma, E, I mean, it's any Borel set in P sigma, P sigma, then corresponding to this, you have this 1E, which is a measurable function. So corresponding to that, you have this 1E. See, this is a, I mean, so you call some element of a C star algebra as a projection if P square equal to P star equal to 1. Sorry, P square equal to P star equal to P. Okay. So the projections in L infinity are precisely these indicator functions. Okay. You can prove that. So when you take the representation of this L infinity, this PE will, this pi of this 1E, this will give a projection in this B of H. Okay. And these projections are what are called spectral projections. Okay. Spectral theorem is something that once you know once you have an operator and once you know the spectrum of it, then using these spectral projections and the spectral projection and spectrum, you should be able to write, you should be able to get back the operator. That's what the spectral theorem is, right? So if you have any normal matrix, okay, then there exist eigenvalues and eigenvectors. And then the matrix is nothing but it's a diagonal matrix with respect to eigenvalues and eigenvectors. We take these eigenvectors as an orthonormal basis. And you have, you can write that sigma t as summation lambda I projection onto, I mean, this is each lambda I will have, I mean, it may have its multiplicity. So there may be multiple eigenvectors. You take all those eigenvectors and that gives a projection. Okay. So this P lambda I will give you a spectral projection. I mean, each has an eigenvalue, and this what I mean to say is this: you can just take it as lambda something. Where lambda is in the, this is a finite dimension. I'm saying lambda is in the spectrum of T. You take any matrix T, a normal matrix or self-adjoint matrix, then you have this lambda of P of T. Then you have, I mean, so in the infinite dimension, it's like a finite function on a finite set. Okay, then any function on a finite set can be written as the indicator function of subsets. Okay, I mean, that's how it is. That's how it will look like. It is summation lambda I indicator function of one singleton, whatever that singleton set. And each singleton set will correspond to a projection, which is this, which is the corresponding to the eigenvalue. You have the eigenvector. You take the eigenspace. You have this projection. And that matrix can be written like this. Okay, this is what spectral theorem or finite dimension. So in infinite dimension, unless it's a compact operator, where you have an eigenvectors, which we have seen, and you can have a countable, you can, I mean, in infinite dimension, if you have a compact operator, which is actually a non-limit of finite rank operators, which is like a finite, which is just a limit of finite rank operator. So you get a countable eigenvectors, and you can write it as summation lambda I one EA, I mean one the spectral projections. Okay, using spectral projections, you can write it. But in general, for a normal operator, you cannot write it in an infinite dimensional space. So for even when H is separable. So what you need is what is called a spectral. You need is what is called a integration, spectral integration. Integration with respect to spectral measure. Okay, you will have a measure which takes values in projections, and using those measure, you will have a spectral. You will have an integral, and you can write that operator as an integral. Okay, it's not summation. Here, any matrix can be written as a summation of some scalar times spectral projection, which you can do for a compact operator also. But if you have a, in general, for a normal operator, you need a you need an integration. Okay, you will get a spectral measure, and those spectral measure is defined. I mean, it's a measure taking values in projections. So, on those projections are called spectral projection. So, I will define what is a spectral projection here. And using those spectral projections, we will prove the spectral theorem for normal operators. Okay. So spectral projections are nothing but if you have any Borel set inside a spectrum, then you can associate the projection using this measurable functional calculus, and that's what is called a spectral projection. But you can define it for general any set in R. So suppose E is contained in, it's an element of Borel projection, and T is a self-adjoint operators. Okay. So sigma of T equal to sigma, which is contained in R. Okay. Then you define, so 1E of T to be that 1E intersection that sigma of T. Okay. So you can define it for any Borel set in R. You take the intersection with this and then define it to be. I mean, it's when it is in the sigma complement, this projection is 0. Okay, as you can see that one sigma is identity, just the identity. Identity. Okay. So this is what is called spectral projections. Okay, 1E are called spectral projections. Okay. And I follow the notation in Sundar's book. ME, so it has some complicated notation. See, the 1E is a function, and the function, I mean, we have the measurable functional calculus, and we use the notation 1E of T as the, he uses this following notation, MT of E, okay, equal to, so the T comes here and the E goes there, which is confusing, but it's okay, which is just the range of 1E. I mean, the range of the spectral projection, which is just contained in H. So this closed subspace, closed sub-Hilbert space is called the spectral subspace or whatever. Okay. Okay. Now we want to prove a lemma. Okay. So before proving the lemma, I want to prove something about positivity. Then I want to prove this lemma. So this is a proposition. Okay, let's make a definition. Okay, let me prove this proposition. Okay. Proposition that T is in B of H. Okay. So there is a small problem in the book. Here he uses something called positivity, then he proves something about positivity later, which I don't think it's nice. We have to prove, because it's not clear whether he's using something there. So we prove positivity here, then I mean we prove something about positivity here, then go ahead with the proposition. Okay, if T is a operator in B of H, okay, then the following are equivalent. 1, Tx x is greater than or equal to 0 for all x in Hilbert space H. Okay. 2, T is self-adjoint. Sigma of T is contained in 0 infinity. It's positive. Spectrum is contained in the positive wavelength. 3. There exists a self-adjoint operator S in B of H such that S square equal to T. Okay. I mean, I'm just assuming self-adjoint because it is only using this proposition we are defining positivity. So I cannot take positivity again. So this is, I mean, any operator satisfying any one of this condition is called a positive operator. That's what I want to say. So this S will be, if S is also positive, then that's what is called a positive square root, and that square root will be unique. We will see that later. Okay. Now, for the purpose of this proposition, I'm just assuming it's self-adjoint. S square equal to T. 4. there exists a, so that is yes, x in V of h such that t equal to x star x. Okay, is also positive. Okay, this, so these are the four conditions which are equivalent. Any operator, any t satisfying, I mean, either one of this condition, then of course it should satisfy all of the condition, is called positive operator. Okay. So this is what is called a positive operator. But then we want to define positivity for C-star algebra also. Okay. So in C-star algebra, we will only use the fourth condition. Okay. Okay. Any x. I mean, we don't have, we have 3 and 4. I mean, we have other conditions also. Except the first condition, we have all the conditions. So, but we will define it through 4. Any x in A satisfying, and we want only the fourth condition. So, any 4 is called positive. Is called positive element. Okay, in the system. We will be dealing with C of x as a C-star algebra, so that's why we need this definition also. Okay. Okay. Anyway, proof of the proposition. The first condition says that txx equal to, is greater than 0. Okay. So we have already proved that if any operator satisfying this is self-adjoint. I mean, we have proved that any, I think in 2 classes before, I think if txx is in R, then T is self-adjoint. We have proved it. Okay. So T is self-adjoint. So because of that, T is self-adjoint. Now we want to prove that the sigma of T is contained in positive real line. So if lambda is in sigma of T, okay, then lambda is an eigenvalue. Okay. Sorry, lambda is an approximate eigenvalue. Which we have proved. So this is equivalent to, I mean, by that we mean there exists xn with norm xn equals 1 and t minus lambda, t is t minus lambda xn goes to 0. Okay. But then lambda times xn, this is equal to lambda, right? But then this goes to, this is equal to lambda. So this limit exists. So this is equal to limit of tx and xn. But then these things are positive. So the limit is also positive. So this implies lambda is 0. Right? Okay. So this we have done earlier. We proved that if T is self-adjoint, then sigma of T, the spectrum of T is contained in real line. We proved. So same proof I'm using, I'm just repeating the same proof for positivity. Okay. When Txx is positive, then T is self-adjoint and sigma of T is contained in positive real line. That's what I'm just repeating that. Okay. Okay. So now T is self-adjoint. So consider the functional calculus. So 2 implies 3. So T is self-adjoint. Okay. So and sigma of T is contained in. We are assuming that T is self-adjoint and sigma of T is contained in 0 infinity. That's the assumption of 2. We want to assume 2 and we want to prove 3. Okay. Then consider the function. Consider the function f in C of sigma such that T going to T power half. Okay, because it's in the sigma of T is contained in 0 infinity, such a square root function exists. So it is a continuous function. Okay. Then T square, this function that f satisfies f square equal to this f naught, right? F naught of t equal to t. Okay. So f of t square equal to f naught of t, but f naught of t is t. I mean, that's how the continuous function calculus is defined. Okay. So take this as yes. Okay. And it's, I mean, this is real value. This t power half is real value. In fact, it's positive value. So because of that, since f of f bar equal to f, okay, f of t star equal to f of t. So f of t, which we calling as s is self-adjoint. Okay, s star equal to s, and then s square equal to t. And we are just using the functional calculus. So this is the nice thing about functional calculus. If you want to, so if you have any function defined on positive real line, maybe trigonometric function, exponential function, logarithm, or any function, whenever you can define that function on the spectrum, okay, then you can define the corresponding operator. Okay. See, earlier, if you have any polynomial, then you can substitute instead of that variable x, you can substitute this operator t, and then you get a polynomial in t. But that's direct. That's just algebra. But here, if you have any continuous function, which can be log function, log or exponential, any function, then you can use this continuous function to define a continuous function of this operator t. Okay, cos of t or sine of t, or, and I mean, if the function is defined in the spectrum, then we can do that. So here the spectrum is contained in positive real line, so we can define the positive square root. We can define the square root. So we have the self, which is again self-adjoint, which is again defined on the positive, which is defined on the real line. So it's self-adjoint. I mean, it takes values in real line. So f bar equal to f. So the functional calculus also is self-adjoint. Okay. So because of that, we have that there is a self-adjoint operator such that s square equal to t. Okay. Okay. So this is the nice thing about functional calculus. So 3 to 4 is clear. You take s itself. Okay. S is self-adjoint. 3 to 4 is clear. The 4 says that there exists x with the t equal to x star x. Okay, take s equal to x, then s square equal to, I mean, then s square equal to t. It's the same thing. Okay? Now 4 implies 1, we have to go. Okay? So if x, s or t, did I write t? T. If t equal to x star x, okay, for some x in p of h, then of course clearly txx equal to x star x, x star x, xx, which is equal to xx, xx. Greater than that. Okay? That's what it is. So the positivity, all the conditions are clear. Okay. Okay. So this is about positivity. So the reason I want to do this is we want to use it for the following reason. Corollary. If pi from any C star algebra from A1 to A2, okay, then pi preserves positivity. Then if x in A1, I mean, this is true for C star algebra. We are using the fourth condition. We are not using the not for Hilbert space. X in A1 is positive. Then pi of x in A2 is also positive. And this is not actually corollary. This is, I mean, if you apply to a positive operator, you can call it. Just a remark. Okay, this is just here. Proof x will look like some z star z, or y star y star y. By definition of positivity, x equal to y star y. Then pi of x will look like pi of y star pi of y, since it is a representation. Okay. Okay. So because so the positivity is preserved. But the point is, if you have a C-star algebra and you have a representation on a Hilbert space, in Hilbert space, the positivity is same as the operator positivity. This Txx greater than 0. Okay, so that's what we are going to use. So if you want to prove a long proposition, so the proposition is following. So I have written here. So this is the proposition we have. So how much time I have? 20 minutes. I may not be able to prove all the 5 points. So let me go through them. So we have defined something for as spectral projections. Okay. So if we have some self-adjoint operator X, and if you have some subset of the spectrum, then we corresponding to that. Yeah. So I thought you were going to ask something. So then we can define a spectral projection. Corresponding to the spectral projection, there is a spectral subspace. Okay. So that we have denoted by something. So if you have a T in B of H, self-adjoint. I mean, we have defined only measurable function, continuous functional calculus and measurable functional calculus for self-adjoint operators. So we are doing this for self-adjoint operators. These things will work for general normal operators also. Okay. So the first one is 1 for X in T A B. Okay, this is nothing but the range of the projection 1, this A B T, right? You have the operator T, which is self-adjoint. Then you have the measurable functional calculus. Using that, you have one ABT you can define. Okay. So if you have a exit that, if you have something in the range of that projection, then A norm x square. If A is positive, then otherwise also it's okay. Is less than or equal to Txx. This whatever we have is less than or equal to B norm x square. Okay. We will prove one by one. Okay. So that you will remember. I don't want to write all the statement and prove one by one. So let's prove one by one. So the proof. What's the proof? So if we have T in AB, okay, then of course T is between A and B. That's what it means. Okay. So let's write this in terms of functions. Okay. 1 AB T. This is a function of T. You multiply that by T. This is less than or equal to B, greater than or equal to A, right? So if T, this just says that if T is in the interval AB, then I mean the whatever you have in the middle, that is non-zero only if if it is 0, then yeah, for all T. Sorry. I mean, if this is for all T, what do I want to write? I want to write it as a statement that if it is not in that, then that becomes 0. This is okay? Is this statement okay? If T is not in that AB, then this becomes 0, right? But then A and B, it will not be greater than A. So what is the right statement you want to write? This is okay. Just no, I just hit everything by 1 AB. Then it makes sense. Okay, then now this is okay. Okay, this is less than or equal to B into 1. Okay, as functions. I have just written it as a functions. Okay, okay. This is true for all t, right? When t is not in AB, all these things become, everything becomes 0. So it's okay. When t is in AB, then this is true. T is in that. Then the middle, whatever in the middle, that function is in AB. The t is in, I mean, that function is greater than A and less than or equal to B. So this is true. Okay. So I didn't define what is, I mean, I define positivity. Is there a gap here? I will define. So if A be a C star algebra, if X and Y are in C star algebra and self-adjoint, they're self-adjoint. Okay. Then this is definition. Okay. Then X is greater than Y if X minus Y is positive. Okay, we can define positivity. So X is greater than Y, then X minus Y is greater than equal to C. Okay. So if pi is in this, then we can actually say that I change the statement. I mean, I'm just saying if you have a representation, then it's order preserving. Okay, then X is greater than Y implies pi of X is greater than pi of Y. Okay, pi is a representation. So you can write X minus Y equal to some Z star, Z star, Z. Okay. Then pi of X minus Y equal to pi of. Okay. So where the definition for greater than or, I mean, we say two self-adjoint elements are greater than or equal, greater than X is greater than or equal to Y if X minus Y is greater than or equal to Y. X minus Y is positive. Okay. Using positivity, we define a partial order on the C star algebra on self-adjoint elements. Okay. So on that order, that partial order is preserved by any representation. Okay. So because of this constant A is A. So A times this 1 AB of the T is less than or equal to this T. I mean, this T going to T, that identity polynomial goes to T. Okay. 1 AB T, which is less than or equal to B of 1 AB. Okay. Oops. Is fine. I'm just using the fact that any representation preserves the order, partial order. And here the representation is a functional calculus, measurable functional calculus. Okay. Okay. Now if X is in whatever X is in MT of AB, whatever you define, which is just the range of 1 AB. Then if you apply, I mean, you just want to apply this TXX. I mean, you apply this inequality for TXX, then you will get A of norm X square equal to X. Okay. So applying this X equation star and star. Okay. You just apply, then A norm X square equal to norm X square is less than or equal to T, what is it? Txx, right? So one thing you should remember is any spectral projection commutes. I mean, this T is an T. L infinity is a commutative C star algebra. Okay, commutative C star algebra, and this T is just the the representation, the measurable functional calculus, which maps the identity polynomial f0 t equal to t. Okay, and this 1ab is something which commutes with that. So this spectral projection will commute with t. Okay? Because spectral projection is just a representation of L infinity. All the spectral projection commutes with that. So if you have a projection 1ab here, you can write it as 1ab square and take it past here and then bring it here. Maybe I'll write it. Okay, but this is just a norm x square. And here you can take this 1abt, which is a projection. You can take, this is equal to its own square. You can bring it here and then take it here. Okay, because it commutes with t, you can take it to the other side. So the whole thing becomes just txx. And 1ab x is x, because that is in the range of that. Is less than or equal to b times x. Okay, so we approve. Okay. Okay. So the second part of the proposition. Second part of the proposition, which just says that x of 1, you take this operator, 0 infinity, maybe is an operator greater than 0. This is just clear. This is just greater than, if you just apply it, call this as t or something. Maybe for x, we want to do. And then we have just, it just follows from you take a equal to 0 and b equal to infinity. B can be anything. Okay. It follows from 1. Here. Okay. Okay, the third one. Is this fine? If you have any problem, you tell me. I hope it's, these are all easy things, but you have to get familiar. If you are already familiar, then it will all be okay. Otherwise, you have to get used to this notation and other thing. I'm not sure whether you are okay with this. Okay. The third one. For all epsilon greater than 0, and x is in this you have to write a set here. I'm just taking this set as T0. You remove this set from R. Okay. This open interval from R. Right? X is in this. Then T minus T naught of X this greater than or equal to epsilon times X. Right? Okay, so for all epsilon greater than this, for all epsilon, no, epsilon, for all epsilon greater than 0 and x is in this subspace, t minus t naught x is greater than epsilon times norm x. Proof. Is this true? It should be just that. Okay, so here I want to give an assignment, I mean, which will make sure you understand this language. So this assignment. Let P be any polynomial, P be a polynomial. Then one of t of e same as one of p of t. This makes sense. So use spectral mapping theorem. Okay. So this is an assignment. You just write down all those things, it will follow. Okay, just you have to write down you are only using the spectral mapping theorem for polynomials. Actually, the spectral mapping theorem is true for continuous function and measurable functions also. But I mean, we'll see that later. I don't know how to do it now. That is, if you have any continuous function, f from some sigma. I mean, if you have a continuous function on f of in sigma of t, c of sigma of t, okay, then sigma of f of t is same as f of sigma of t. This is true. Okay, we will come to this later, but you don't have to use that. You use the spectral mapping theorem or polynomials, which we have proved for Banach algebras. Okay, then 1t, this makes sense. If you have any for E in so if you have any subset of I mean E is the Borel subset of sigma of t, then 1t of E makes sense. Sorry, 1e of t. This is the confusion. E of t. So then we have that P of sigma of t. P of sigma of t is same as sigma of P of t, right? So if E is a subset of sigma of t, then P of E is a subset of sigma of P of t. Okay, so this makes sense. These two make sense, and you have to prove that these two projections are same. Okay, so once you prove this for me, once you prove this assignment, then it follows easily. So one of t minus t naught square. Okay, this is a polynomial in t. Okay, of any. So whatever that set, what is that set? that set is we'll write the other way. 1. So we want to prove this the inequality. So for that 1, this set is R minus T naught minus epsilon, T naught plus epsilon, okay, of T. This is equal to the same projection 1 of. So if you shift it by epsilon and then take the square, this is just epsilon square infinity, okay, of T minus T naught square. Okay. This is just you just apply this assignment, then you get this. Right? Now if x is in whatever, that x is in that m of this, then we have that I mean, we have proved in the work. It follows from 1. The square is greater than epsilon times x. That's what we do. I'll stop here. I will recall all these things and then I will prove more things about spectral projections. Then there is then we will use a family of self-adjoint operators and prove something, prove the spectral mapping theorem for that. Use that to prove, I mean, every normal operator consists of 2 self-adjoint operators. Every normal operator, x looks like t plus is, okay, where t and s are self-adjoint and they commute. When they are normal operators, they commute. So if we prove for some commuting family of self-adjoint operators, some spectral mapping theorem, you can take polynomials in multivariable. Okay, then you can prove the spectral mapping theorem for multivariable thing. So then I mean, for continuous functions also. Then we use that to prove spectral mapping theorem for normal operators. So that's our game. Okay. For that, we need some more tools, and we use the spectral projection and all those things. Okay. So I stop here. If you have any doubt, you ask me. Okay. If no one has any doubt, I'll stop here. You can ask me later.